As you may have guessed it, we're gonna see the rhythm of the logs, that is logarithms, or log for short. Hi, I am Matt. And before we dig deep into log, let's have a quick review of laws of indices and power functions. The common indices we've seen are expressed using any number, like n to the power x, and then we multiply it to n to power y, which equals n to power x plus y. 1 upon n to the power x is n to power negative x. And what if there is a power to the power such as n to power x to power y or n to power y to power x? In both cases, we get n to power x multiplied by y. Moving forward, we see n to power x divided by n to power y, which comes as n to power x minus y. And lastly, any number n to power 0 is always 1. And n to power 1 is the number n itself. These were the basic properties of indices. Remember these last two, we might need them later on. As for the power function, we will see them using examples.
2 power 2 is 4, 2 power 3 is 8, 2 power 4 is 16. And so on. Nothing new.
But here we can almost see a new function born
from this table, that is, b to the power x equals y, where x is the power, or the exponent, b is base and y is the argument.
Now using the same function we can find missing elements in the following problem, where 2 to the power what? Is 128. And the answer obviously comes as 7. But wait, can we really solve any and every problem using this method? That too without using a calculator? Makes me wonder every time. Why won't we need a calculator? One would ask. Some exams do not allow the use of a calculator. Or by some coincidence, a massive explosion happens to send an EMP surge, resulting in the failure of operation of any and every electronic device on the planet. If this happened to you, then knowing how to use log might come in handy. Let's take the previous example of 10 to the power of what is 17.5. How log helps us solve this is shown with a mathematical form of the log function, where the base goes below the log function and the argument is being operated by log, and the exponent, or power, will go to the right side as an only unknown part of the equation. So with what we all know until now, we can clearly state the definition of the logarithm as the inverse of power function. And the mathematical expression can be given as log to the base b, y equals x. Now to find the log of 17.5. We need to learn how to read the log table, which looks somewhat like this. First, we will take the fraction number and rewrite it as a multiple of 10. Rewrite in such a way that we always get decimal after the first digit. And multiple of a power of 10. And the power of 10, which is 1 in this case, is called the characteristic. The number 1750 is now to be scanned through a logbook. First two digits are 1 and 7. So we look for 17 on the leftmost column, where we can see 17 on the left side column, and we stick to that row of 17. We see the third digit as 5 here, and see the third digit 5 on the log table's top, and stick to the numbers in that respective column. Both 17's row and 5's column will cross at a distinct number, which is 2430 in this case. Since there is no fourth digit here, we don't need the mean difference table. Don't worry. We will also cover this part of the log table, but in the further segment. The number 2430 we found using the log table is now rewritten as 0.2430, and this is called the mantissa. Now to get our final answer, we add both characteristic and mantissa together, and the answer to the log of 17.5 is 1.2430. We originally needed the power of 10, which will give us 17.5 as result. And using log table we have found the answer as 1.2430. We can cross-check our answer using a scientific calculator, and here we see the answer is 17.49. Which is close enough we can get faster and without using a calculator. We will go into depth on how to use a log table and the anti-log table. But for now, we will just go on with the knowledge that we can easily find the power to any number to give a specific result without using a calculator.
One concept which I would love to share with you is the revision sheet. Revision sheet is nothing but a list of formulae, tricks, notes, and important problems written down on a sheet.
Having and maintaining such a sheet, especially for learning mathematics, is very useful. It will definitely boost confidence and keep the morale high, and yes, obviously help you with the revision of what you've learned previously. The revision markers for this topic so far can easily be the definition of the log and its mathematical expression. Now it's time to be familiarized with the laws, types, rules, and basic properties of logarithm. For the first basic property, I am going to need you to remember those two laws of indices that I had pointed out earlier. Yes, the ones that state any number n to the power of 0 is always 1, and any number n to the power of 1 is the number itself. These two will help us form the basic properties of logs. We do know how to change an exponential function into a logarithmic one. Just like we derive the mathematical expression of log from an exponential function, just like this. Using this same method, we can transform the above two equations as log of 1 to the base of any number n which is always equal to 0, and log of any number n to the same base n which is always 1. So, when we see log of 1 to any base, be it 1, 2, or 3, or any number for that matter, the answer is always 0. And when we see log of any number with the same base, like log of 1 to the base 1, or log of 2 to the base 2, the answer is always 1. Time for a quick revision sheet update. The two new properties of the logarithm, which we've just learned, do deserve their place on this paper. On to the next one. The most familiar types of logs we will use are common logarithm and natural logarithm. And what are these common and natural logs? We will see right away. All logs that have base as 10 are common logarithm, and all logs that have e as base are natural logarithm. Which means the inverse of the common log is a 10 to a power function. And the inverse of the natural log, an exponential function. Exponential function, you say? You might be wondering, what is e? Some of you learning log for the first time are also unfamiliar with what an exponential function is, apart from hearing about it in movies and TV shows from time to time. E represents radioactive decay, and is named Euler function after the mathematician, Leonhard Euler. Its mathematical expression is given as follows. E is an irrational number, however for approximation we round it off to 2.718281828. 45904. That's it. Back to our distinction. All the results in log tables we see are common logarithms results. Meaning the values in log tables which we see are common logarithm results. As for natural logs, they are majorly used in solving calculus problems like differentiation and integration, and sometimes natural log is written as ln. Note that whenever a log is mentioned, and the base is not, then we assume the base to be always e. In other words, when a base is not mentioned in a log, then that log is always considered as a natural log. The interesting thing about common and natural logs is that they are interchangeable. And what I mean by that can be seen in the following examples. Let's take the log of a number, say 25, with base 10, and we take the log of 25 again, but this time with base e. For speed reasons, I will use a calculator to solve these. As expected, we do get different answers. To be sure of our results, we need to do the same operation again, but this time with a different number, say 70. Now, if we multiply 2.303 to both of the common log results, we get a near approximation of the natural log results, which is safe enough for us to state that, if we multiply 2.303 to the common log of a number, we get the result same as taking the natural log of that same number. Let's grab a fresh new paper for our revision sheet. This one seems to have very little space, and mention the relation between common and natural log. Moving on to laws of logarithm. In other words, LOL. We are going to see 4 important laws, and their variations more or less, that are going to help us understand logs better. First off, we have log of power. This law helps us to realize that when taking log of any number, m, for instance, with a power n, we can take away the power of m, that is n, and multiply this n to the log of m, saving us the hustle to find m to power n. In technical terms, the logarithm of a power of m is equal to the exponent of that power times the logarithm of m. To see this law's proof, we need to get down to basic examples and see it for ourselves. Let's take log of 8, which comes out as 0.9031, and then we take log of 64, which comes out as 1.8062. We can clearly see that, if we double the log of 8, we get the same result as log of 64. So, if instead of log of 64, we wrote log of 8 squared, then we can easily reduce our efforts by just taking the power of 8, which is 2, out of the log operation and just multiplying it back to log of 8. But, beware. If you see log to base b, of any number m, to the power of n, and rewrite it as, n multiplied by, log to base b, of m, then you might be right. But, what if, that n, is not just the power of m, it is the power of the entire equation, including log? Then this law won't be applicable. And this is what we must look out for and try to avoid this completely. Because, every time we do this mistake, a baby bunny cries. Moving on to our next LOL, the log of product, which states that product of numbers that are difficult and time-consuming can be simplified by using logarithm, by converting multiplication into simple addition. In technical terms, we can say the logarithm of a product is equal to the sum of the logarithms of each factor. Here, each factor is a noteworthy mention. As we can see, this statement holds true, even when there are multiple multiplications involved, which further can be turned into multiple additions. Moving ahead to see the proof of this LOL, we use 2 numbers, m and n, where m is b to power p, and n is b to power q. And their respective logs can be given as follows. And we state this as equation number 1. Now we multiply m and n. And as we had seen earlier, in laws of indices, product of 2 same numbers with different powers leads to the addition of their powers. Now we apply log to the entire equation. Dropping the power down, we see the properties we've learned before come into action. We use the law of log of power to move p plus q from power. And log of b to base b gives us 1, as the log of a number with same base is always 1, which gives us log m multiplied by n equal to p plus q. And now, recalling back to equation 1, and resubstituting their values, we finally can give the proof of this law. But beware. While we do know, a multiplication operation can be done quickly by using log, by just simply adding the numbers. There is no formula or shortcut available for another way around, meaning if we see the addition of 2 or more numbers such as m, and n, we don't have any new formula for that, we don't have any option other than to solve the addition first, and then apply the log, and many people do this mistake here, thinking that there must be a shortcut to solve this. Here only knowing the right way is not enough, we must also know which is the wrong way. And we must absolutely avoid these mistakes at any cost, because every time we do these mistakes, a baby bunny cries. Moving on to our third LOL, log of the quotient, which helps us take the long division, which is of course again time consuming, can be further simplified by using logs, which then converts it into a simple subtraction operation. In technical terms, we can say, the logarithm of a quotient is equal to the logarithm of the numerator minus the logarithm of the denominator. We will prove this law using the same method we used to prove log of product. We use two numbers, m and n, where m is b to power p and n is b to power q, and their respective logs can be given as follows. And we state this as equation number 1. Now we divide m and n. And as we had seen earlier in laws of indices, division of two same numbers with different powers leads to subtraction of their powers. Now apply log to the entire equation. Dropping the power down, and taking log of b to base b as 1, we are left with log m divided by n equal to p minus q. And now recalling back to equation 1, we can resubstitute values of p and q to give us the proof of this law. But beware. Again, log of m divided by n is log m minus log n. But sometimes some people do the mistake of taking log of numerator and denominator, and not substitute division with subtraction, which is of course so wrong. And because of this, a baby bunny cries. We can use these laws to create new formulae, which will give us more shortcuts helping us solve logs even faster. One such new formula is log to base b of 1 upon any number n, which can be rewritten as log to base b of same number n multiplied by minus 1. And to prove this, we use law of quotient. The log of 1 upon n, we get log 1 minus log n, and since we know a log of 1 to any base is always 0, we only get minus of log to base b of n. How we can implement this is seen in the following examples. Log of 1 upon 7 is minus log of 7, and log of 1 upon 5 is minus log of 5. Another such new formula can be formed, using both log of product and log of quotient. Using log of base b of m, multiplied by n, upon o, multiplied by p, which can be rewritten as log of m, multiplied by n, minus log of o, multiplied by p. Which can be further simplified as, log of m, plus log of n, minus log of o, minus log of p. An example of this formula can be seen as, log of 2, plus log of 9, minus log of 8, minus log of 3, which is rewritten as, log of 2, multiplied by 9, upon 8, multiplied by 3. Simplifying them, we are left with log of 3 upon 4, which is easier to solve, because we have a lot less calculation to do. Moving on to our final LOL, and probably the most important law. This law makes log so malleable and flexible like it's the queen piece in chess. The rule of change of base. This law states that, in a log, the base can be replaced with another one, by placing the existing base as the denominator. But, on condition that the existing base and the number we are taking log of are not 1, and are positive and real numbers. And the new base is compatible with log, meaning the new base should not be 0 or 1. Let me demonstrate how this law works. Suppose you need to find a natural log, that is log of e, of any number, but you only have your log table with you. So what we will do here is take log of base 10 of that number, upon the log of base 10 of e, that is the previous base. And we can calculate the log of base 10 of e, using the log table, and the answer comes as 0.4343. And solving the fraction of 1 upon 0.4343, we get 2.303. This number is really giving me some serious flashbacks. That's right. This entire equation is the relation between common and natural log, which not only proves this law inevitably, but also gives us another proof of how we can interchange between natural and common log. We can get a new formula, using the rule of change of base, for easier calculations. The first thing we do here is to take the numerator, and place it as the denominator of the denominator. The base change rule is not just a one-way door, it opens both ways, meaning if we can remove the base from a log, we can also assimilate 1 in it too. So we get log to base m of b as a new log in the denominator. What new interesting thing we've seen here is that we can easily manipulate the position of base and the number in a given log. And what if we take the log on the denominator and multiply it to log on the right side? We get a new variation of the base change rule to work with. Another new formula we can conjure up using base change rule is this one. Log of m to power n to base b to the same power n equals 2 log of m to base b. First we will take the left side of the equation and apply base change rule to it. The new base we add is c. Now we use our first law, the log of power, to remove the power from both the numerator and the denominator. And after cancelling out the n's, what we are left with is log of m upon log of b. Now using base change rule we can take this equation and state it as log of base b of m, which does match with the left-hand side. Practically this formula does help a ton with big power problems, especially when we are not allowed to use a calculator. Like in this problem here. Log of 343 to base of 1000, this problem can be solved using the base change rule where we separate the base and solve log of 343 to base 10, and log of 1000 to base 10, separately, which is evidently easy, but it can be easier. We can use this new formula and rewrite the equation as log of 7 cubed to base 10 cubed, and then cancel out the cube altogether, which just leaves us with log of 7. Let's revisit the revision sheet and update it for all the LOLs we've learned. The first one, law of power of log. Second, the law of product. The third one, the law of quotient. And finally, the base change rule. New manipulated formulae or corollaries also deserve to be mentioned here. And some more corollaries. These are some of the most commonly used log tricks, in general. The log of b to base b to power x makes the log redundant. And the power, which is x here, stands alone. The same goes with log of e to base e and also with log of 10 to base 10. Since this result is true in log format, it must also be true in an exponential format. So we have b to the power of log to base b of x, which results in x standing alone, making the exponential function redundant. The same is the case with e power of log e, and with 10 power of log 10. I guess that's enough with the theory, time to solve some problems.